Hello, and today I'm going to be talking about the synthesis of dibenzalacetone from acetone and benzaldehyde through a double mixed aldol condensation reaction. Now, aldol condensation reactions are a subset of aldol reactions in which we take that beta hydroxy ketone that's normally formed, but then we further react it to form an alpha beta unsaturated ketone. And I say ketone in this case because the final product of this particular synthesis is a ketone molecule. In this case, we're going to do all of this in base catalyzed conditions with 3 molar sodium hydroxide. This 3 molar sodium hydroxide is going to first deprotonate the alpha position of the acetone in order to form an inulate with acetone. And that's going to go through the reaction mechanism until we get to the beta hydroxy ketone intermediate, which is going to be further deprotonated at the alpha position in order to form the alpha beta double bond. And then this reaction will be repeated again in order to form the di-substituted product. We're going to need water as well to protonate an intermediate alkoxide molecule that forms within the mechanism. And in order to mix these polar and non-polar elements of the reaction, we're going to use ethanol because it is commonly used to help the interaction between polar and non-polar components of these types of synthesis. And to do this, we're going to undergo the mechanism, which I'm going to show you here on my trusty little whiteboard. So to start this mechanism off, we're going to have deprotonation of the alpha position on an acetone molecule using hydroxide, which is going to form the resonance stabilized intermediate. As you can see, the negative charge is stabilized between the oxygen and that alpha carbon that we deprotonated. And this is important because that carboanion that we formed is going to go through a nucleophilic acyl substitution reaction with that slightly more electrophilic aldehyde. This is going to help form that alkoxide intermediate that I discussed earlier, which is going to be protonated by a molecule of water to form the beta hydroxy ketone. However, this only completes the aldol portion of the aldol condensation reaction. And in order to complete the condensation, we're going to have to again deprotonate at the alpha position. This is going to form a carboanion intermediate. And these electrons are then going to go to empty pi orbitals at the alpha beta bond in order to stabilize the structure. This is going to promote the expulsion of OH as a leaving group, giving us benzalacetone. And all we have to do now is we're going to do a repeat of the above steps utilizing this alpha position now on the acetone, and then that's going to give us our dibenzalacetone. Now, there's a couple things that we have to consider before we do this reaction, one of which is that we're going to need that excess of sodium hydroxide in order to mediate both the formation of the inulate and the formation of the double bond in a timely and efficient manner. That's why we're using 3 molar sodium hydroxide. And when you'll see when I talk about the procedure, we're going to use a lot of this. Also, we need to consider the fact that if it has alpha protons, meaning the carbonyl compounds, they're going to form inulates. So that's why benzaldehyde has no alpha protons. So that way acetone is the only species that can form the inulate. However, you can also argue that acetone will just react with itself and we're going to get a mixed batch of products. But when I get to the procedure, I'm going to show you how we mitigate that during the synthesis. So now that we went through the theory as well as the mechanism, let's talk about the procedure. So to start off the synthesis, we're going to have a 4-part 3 molar sodium hydroxide, 3-part ethanol, and 3-part water solvent mixture go into a flask along with a stir rod. This is going to be put on a stir plate and it's going to be starting to stir. Then we're going to add 2.2 parts benzaldehyde per 1 part acetone, which was about 2.8 milliliters. And the reason we do this is, for one, aldehydes like to oxidize into carboxylic acids, specifically carboxylic salts under these conditions. So we have to have enough to where we're going to still have benzyl aldehyde to react. Second, you need at least 2 moles of benzyl aldehyde per 1 mole of acetone in order to get the di-substituted product. So that's just basic stoichiochemistry. And third, we want this reaction to occur at a decent rate. Just like with the sodium hydroxide, we need to have enough to where this reaction is pushed forward in a reasonable time frame. Now that we've added the benzyl aldehyde, then we're going to add about 0.91 milliliters of acetone. With it being the limiting reagent and being added last, it's more likely that it's now going to react with a molecule of benzyl aldehyde than with another molecule of acetone, mitigating that problem that we discussed previously when we were on the mechanism. Now, once this reacts for about 30 minutes, you'll start to see the formation of a yellow coloration. That's the first bit of product forming, and it's dissolving in the solution. However, as more product forms, it starts to oversaturate our reaction solution, and it falls out as precipitate. What we're going to do after the synthesis step is we're going to wash this precipitate by first adding 20 milliliters of deionized water, putting it through vacuum filtration, and then washing residual polar reagents or impurities or byproducts off with 3 50 milliliter portions of deionized water in a wash step. This crude product will then be dried as best as we can before recrystallizing it, going through a recrystallization with ethanol or an ethanol water mix. This purified product will then be dried before we analyze it with FTIR spectrum, 1H NMR spectrums, melting point range, and a percent yield. Now, melting point range, to start off, was about 80 to 120 degrees C, which is within the range of dibenzalacetone. Your IR spectrums are 2,000 to 1,800 inverse centimeters, which was our aromatic ring. That's very common motif. We had one at 1650, which was a very intense peak for the alkenes, which makes sense due to the conjugation of the molecule. And then we had one at 1580, which was the carbonyl, which was also very intense, which makes sense due to the electrostatic effects of acting on that carbonyl group. And that conjugation also helps to push that reaction forward because that's a very stable molecule. And all molecules are trying to go from unstable high energy states to more stable low energy states. And that's also why we experienced a pretty high percent yield at greater than 99.9%. And we can also see this structure represented in the 1H NMR spectrum, where we had 3 doublet peaks, which would correspond with methylene or methylene hydrogens, which is your CH, which is what you would expect in double bond chemistry. We saw this at 6.9, 7.1, and we saw the aromatic double bonded hydrogens at 7.9. And between 7.4 and 7.8, that's where we saw the doublet of doublet peaks, which would be characteristics of the aromatic rings. So all of that data showed that the synthesis was successful, and we got dibenzyl acetone, and we got it at high yields. So the next question that a lot of us are probably asking is, what does this matter? Why are aldol condensation reactions so important that we need to do a whole lab on it to get an idea of how it works? Well, for one, this is an important reaction in medicine. I've read several papers now that show a link between the enzymatic aldol or retroaldol reactions of benzylamine into benzyl aldehyde and hydrogen peroxide. Now, this isn't exactly an aldol condensation, but it does show the importance of these types of reactions in the fact that benzyl aldehyde has been shown as a molecule that mimics insulin in glucose regulation and also plays a role in suppressing lipolysis, which can help with cholesterol and other lipid profiles within the blood. This is very important for patients who have diabetes mellitus, where these are common issues, especially when you're on high-fat diets. And a lot of these studies have been done in high-fat mice. And there's also the use of aldol condensation reactions in citrate synthase, where oxaloacetate reacts with acetyl-CoA through an enol intermediate in acid catalyzed conditions with charged amino acids in order to form cityl-CoA. This is an aldol condensation because we're forming double bonds. We're forming beta hydroxy ketone groups, and they're reacting under nucleophilic acyl substitution reactions. So in conclusion, this was my take on the synthesis of dibenzalacetone. I hope you enjoyed it, and thank you.